Good morning, everybody. My name is Matthew Armand. I'm a production engineer at Facebook, and I'm here to talk to you about server provisioning in an IPv6 only world. Before I could actually go into the actual main part of the talk, I want to talk about, I want to actually ask a couple of questions. Of you in the room, who has services that are dual stacked currently? Publicly facing, excellent. That's awesome. This helps drive adoption with IPv6 in general. Those people, who runs their own infrastructure as opposed to using a public cloud? All right, excellent. Who has IPv6 only in their data centers? That's what I thought. Okay. Okay, so the question is, why would you do this? Are we crazy? The main reason for doing this is for simpler routing. Facebook obviously has got to a reasonably good size, and we decided whether to go dual stacked or go to v6 only fairly early on, a few years ago. And we decided that long-term v6 only is the right path. And so to support this long-term, we made a goal to actually go v6 only in our data centers. And today we are a combination of dual stack and v6 only. But we've been doing v6 only clusters for just over a year now, since the start of 2015. And the stuff we learned, we figured that when we started this process, we learned a lot of things along the way, and lots of things, as you've probably experienced with v6, were broken initially. And hopefully some of the things you've learned from my talk, you'll be able to take in and then apply to your own environments. So I want to talk very, very briefly about Facebook's structure a bit, and then review the way that v4 provisioning works on bare metal, and then what's different about this, and what we learned about it. And then at the end, I got some conclusions for you. All right. So internally, Facebook's data centers are pretty flat. We have a whole bunch of racks. Every rack has a top of rack switch, and every server can pretty much talk to every other server. So in this particular picture, the server on the left provisioning, that's the one that actually wants to be installed with a new OS, and it uses services from other servers in other racks and other data centers, sometimes close, sometimes far away. The topology doesn't matter so much. The only thing that's slightly special is DHCP, because we use Anycast for that. Everything else is like discovered by some kind of service discovery. Looking more specifically, we have our top of rack switches are actually routers. Every rack is its own subnet, and this presents some interesting problems for us. In that everything that uses IPv6 has to have routing working, and this is really quite important. Your networks may not be quite as strict as this. They may have slightly different boundaries, but if you have any routing at all, and you have servers that are being provisioned on the other side of another router, you may have some of the same problems that we had. Also, something to note, because we don't run public cloud stuff, all of our servers have basically two systems in them, the main server itself and then an out-of-band or base management controller. They're on the same network. One thing we can do at scale is when we get servers delivered to us or built for us, we can have some specific changes. What we do is we actually require all of our servers to be set to boot from network from the factory, which is very useful. I couldn't imagine going around plugging a keyboard and mouse in and pressing F12 at everyone to actually install them. So in this case, these servers are set to boot from v6 first, and then v4 if they're plugged into an older cluster, and then hard drive. Also, I won't go into this much detail, but because our base management controller or out-of-band controller, I'll call it BMC for short, or OOB, it's the same thing. Those have to have good v6 support, because to actually manage these servers, you need to be able to power cycle them reliably, and also it's useful to have console access. At Facebook, all of our servers are given a IP address when it's first provisioned, a single address. We have dynamic routing, which means that in v6, we use router advertisements to learn the route for a given server. And we use DHCP to actually provide the statically assigned address to the servers when they're being provisioned. Also, the out-of-band controller is configured only via DHCP. This allows us, when we move hardware between racks or between other data centers, not having to reconfigure them each time. That said, once our servers are installed, they will have a static network configuration. So if there was a major outage, you can just reboot the server and it will come back up normally. All right, so why do we do this? Well, all our servers have names, and so we put them in DNS, so they have to have a name to IP address mapping. And we have a service discovery system, or service discovery, which also keeps record of like a particular IP address as part of a larger list of services. One thing we do not use at Facebook is stateless auto-configuration. This is a very nice feature about IPv6, which allows a machine to automatically determine its own IP address without the help of a DHCP server. But it's actually unhelpful in that when you run services, you can't predict the IP address of that host, not without knowing the MAC address of that machine. And if you do repairs and you change the hardware, that can change. So that will really mess you up. So we turn it off. All right. So how does provisioning generally work on PC-type hardware? You tend to reboot them. Then you boot into the BIOS. The BIOS has a thing called PXE. PXE is a combination of two pieces. The BIOS will do a DHCP request and ask for an IP address and a couple other fields. One of those is the TFTP server, and then you can download a file, whatever file it's been given from the DHCP server, and typically it's given a bootloader. The bootloader provides a nice level of abstraction because on Linux systems, you tend to want a kernel, RAM disk, and a whole bunch of command line parameters. So once you've got those things, you load them into memory, and then you execute the kernel. Then you can use your installer. In our case, we use CentOS, so it's Anaconda. And once it's installed, you reboot, and you can run something like configuration management. So what happens when you go to v6? Well, the requirements change a little bit. The most important part is the firmware difference. Most machines shipped these days have UEFI, Unified Extensible Firmware Interface. It's a bit of a mouthful. This has good support for IPv6, and will allow it to do the same function as PXE, but over that. The other difference is the way DHCP works. In DHCPv4, you get both the address and routing information in one go. On DHCPv6, the standard setup is that you ask for an address and other parameters via DHCP, but you don't actually get any routing information. The intent is that you use router advertisements instead. What doesn't change is TFTP, which is a terrible, terrible protocol. And although the spec mentions possibly using HTTP, we haven't actually seen any machines which actually advertise this behavior. We decided not to pursue it. We had bigger fish to fry. All right, so because we have a default route, the DHCP v4 has an external plus file name, and v6 it turns into a URL, which is nice because you can specify port numbers. Not really relevant to this. For an example network configuration for your router, we actually do a few things that are different to the defaults. We turn on managed and other flags. Managed and tells things like an out-of-band controller to use DHCP instead of Slack. Other means there's other configuration available, like DNS servers. This is mostly for things other than the server itself. One of the most interesting things is that we actually changed the router advertisement interval to a very aggressive every 4 seconds, which seems a bit crazy, but it actually turns out to be really useful later on. Relatively short lifetime, and there is a DHCP relay because DHCP works by broadcasting or in the case of v6, it works by doing a, is it multicast? Anyway, it basically shouts in a similar way, and the rack switch or other router has to forward this to some other service. What we found is that support for DHCP is actually not as good as support for actual general IPv6. So although you may have a functioning v6 network, this bit may not work very well. So that's useful to know. For our environment, we've been using Kier, ISC's Kier, with a plugin for looking at data in our own database. Every server, when it's first brought in, we know the MAC address of the machine, we know the IP address that we're going to give it, and this allows us to do a call into our asset database and actually discover, given a given request, what IP address should I serve? Also, what should I provision it with, or should I provision it at all? I won't go into the mechanics of that, but that's not different. There's a good presentation that one of my colleagues did on this. Angelo talked about the infrastructure of that, so I encourage you to watch that if you can. Here's the really tricky part, server identity. In IPv4, the most common way for a server to be identified is by a MAC address, or its hardware address. In v6, the specification changed because one of the downsides to using the MAC address is that people change network cards, and the server identity changes. So if you don't have a good track inventory about what you have, the MAC address changing means it looks like a brand new device. In the case of Facebook, however, we have a very good repair workflow. So if we do change network cards, or we do expect the MAC address to be different, we do update that. So it actually worked against us. And there are several methods to identify a server. The DUID is the DHCP unique identifier. It's meant to be an opaque value, just some value you see, and if a server requests again, you know it's the same server. Two of the most common ones are either LL or LLT, link local or link local plus timestamp. These are both derived from the MAC addresses of those servers. The link local plus timestamp is interesting because if you have a machine which has a network card in it, and later on you change the network card, it can basically keep the same identity as it did before. The timestamp plus the MAC address are combined as a single opaque value. And that means that later, if you put that same NIC into another machine, it will have a different timestamp and therefore have a different value. If you have, the other thing that's interesting about this is that this is a device identifier. It tells you about the whole server, not about which network interface was used. So if you have two network cards, you may get a value which is derived from the other NIC, which is a little bit surprising. All right. The other part that's tricky is that if you are doing DHCP in multiple locations, different DHCP clients will use different identifiers for exactly the same hardware. So example of one of our servers, there's two network cards on here. The one on board, which likely isn't used, would likely have an LL, which, because that's directly tied to the actual physical implementation of that machine, it would not change, and therefore it could be reliably used. If it's a network card that's plugged in, like that mezzanine card, it's likely to be LLT. I should go back in a second. The enterprise number one is very rarely used, I've seen. That one is meant to be a way to have systems enumerated by the manufacturer, and the UID is used on some machines. In reality, at Facebook, we actually have requested all of our machines be either LL or LLT. All right. So what did we do at Facebook? Well, we basically cheated. Because we know the MAC addresses of all of our machines, so we can rely upon that, we want to keep the workflow very similar to what we did with the IPv4. We have a very small bias modification that means that every time the machine is powered on or there's a request, the timestamp is reset or the persistent information is lost. So every time the part of the opaque value is the MAC address, is always the MAC address of the machine that you actually have, of the network card you have. And they also guarantee, in our case, that the MAC address comes from the interface doing the request rather than the one on motherboard, for example. And the really tricky part is that these opaque values are meant to be just done for equality. We actually look inside the values to actually work out what the MAC address is, and we actually use that to determine the identity of the server. Next step, TFTP. That was interesting too. We had buggy firmware. One thing we found was when our servers were turned on and they made DHCP requests, that worked fine. We made a TFTP request, nothing happened. Why was this? It's because the server learned the IP address just fine, but it wouldn't wait or didn't properly do the request for a route. And all the testing in the labs had been done with the TFTP server, the same subnet. And when he got /64, he was like, why wouldn't it be in the same subnet? So that was a big problem for us. So what did we do to do this? We made a little setting called horribly hacked clusters, where we had hardware of this type. We did a terrible trick. We used on our wedge switches, we used a Python-based TFTP proxy. We'd actually use an IP address inside that subnet and forward the request outside of it. It was really unreliable, unfortunately, but it allowed us to get us through a time period while the firmware was actually fixed. And the reference one is now, I think the Intel maintains this. If you have this problem, there ought to be a BIOS upgrade that can fix this for you. Okay, the grub loader, the bootloader we use is grub. We like it because it's very widely used for booting from local hard drives. It also has fairly good support for booting from network. But we have found some minor issues with it, but we've been contributing some patches upstream for that. We download a config file dynamically, and then we download multiple files. And one of the really awesome things about grub is it supports HTTP. So if you've got a large kernel or RAM disk combination, and you're running a server in a remote location, some of our pop locations are, we don't have provisioning infrastructure in the same place. It has to go remote. It means that you don't pay the TFTP penalty of the bandwidth display product. All right. So we went through 2 phases of this. When we first got a full cluster of machines like this, we kind of went into war room, and we figured out, despite the hardware technically supporting all this, we had to actually go through and make it work for real, because otherwise we couldn't use those machines. And at the time, we were using CentOS 6 and Anaconda 13. And what we did was fairly unpleasant. We took the RAM disk apart. We found bits of code that were fixed one way or the other. There was some v6 support in there, but we found that when we took away the v4, it didn't actually work. So we just did enough to make it work, and then we packaged it back up and crossed our fingers and got on with our life. It was better to be done than be absolutely perfect at the time. It bought us some time to then look at the problem more carefully later. So, okay. So later on, a few months later, we looked at using CentOS 7, and we actually found that the CentOS 7 has a much newer version of Anaconda, basically a rewrite. We knew this at the start, but we had dependencies upon Anaconda 13 at the time. So we took that, and we decided to actually document what we found. And some of the things, hopefully all the things that we found really are either fixed or documented here. We also found, interestingly, that you can install CentOS 6 with it, with any minor changes, basically to install a different version of grub. So all our problems with the installer came about because of the number of steps involved in actually setting up the network. In pretty much every circumstance, you go from not configured to configured in one step. But when you have IPv6 and you're doing static addressing, but using dynamic routes, you end up with a situation where you go from no network configuration to having the network configured or the IP address assigned, but the routing not working. And then only after a router solicitation or router advertisement has been received can you actually talk to anything outside of that subnet. And this is basically the crux of most of the problems we've had. So there's two pieces to Anaconda. There's a RAM disk called, which uses Dracut, minimal Linux system. And we basically added a 4-second delay after the network was set up to allow the router advertisement to work. That works really well. In the second part of Anaconda, which is the stage 2, it uses Network Manager. And that currently doesn't allow a mixture of static addressing and dynamic routes. We have a bug open on this. We're likely to probably contribute to fix this. However, in the short term, we've got a very simple and dumb fix for this, which basically says in the prescript, force on accept RA a lot. And if you do that, you will learn your routes and you'll be fine. Network Manager also is used, well, the Anaconda looks at the state of the network from a Network Manager, and there are multiple states that Network Manager can tell you. And there's basically no configuration, link local, site local, and then global. And it treats anything other than not connected as connected. So it doesn't actually distinguish between the two. In our case, just adding a delay here basically fixes that. So simple, dumb, but it works. So at Facebook, most of the work was done in 2014, about summer of, and we did a couple of clusters like this. But in 2015, in January, we made a point of actually going forwards with only IPv6 capable hardware and using IPv6 only installs. If you want to do the same, be practical. Make sure your v6 works properly first. Nothing worse than trying to debug two problems, whether your v6 itself is working or whether your provisioning is working. And your environment, so your requirements may be quite different to ours, but if you understand your DUID situation, you actually test this out, you'll have a better idea about how to handle your inventory or server discovery mechanisms and move forward with that. Your rack switches, even if they support v6 well, may have DHCP problems. And I encourage you that even if you don't need it today, you should actually test your hardware, and then you can make a good decision about what you are going to buy next or what you're going to do next in the future. And that is it. All right.
How did or do you keep your application or higher level software tested to the point that you know you're not introducing or harboring IPv4 specific dependencies?
Is it related to provisioning or in general v6 versus v4?
Well, I'm assuming that the point of provisioning these systems is so that you can run Facebook on them. So
yes,
was there like a long period of time after you succeeded at the provisioning level where the cluster or
we'd actually been
useless?
We've been running dual stacked, and we do traffic analysis to ensure that the majority of traffic went over v6. Actually, I think like in second quarter of 2015, we actually changed most of our developers to use v6 only dev servers, and that's actually. It was brutal, but it was it helped people empathize with the fact whether they're writing software for v4 or v6. Okay, cool.
I was curious, how did Network Manager end up in this mix of things?
It's part of the CentOS installer. It's not absolutely perfect, but it is a very good starting point for. We don't feel like it's worth rewriting a network installer. So Network Manager is part of CentOS 7 by default, and the installer actually uses this in stage 2 to configure networking, and does on I think running CentOS 7 system, although you can opt out of it on CentOS 7.
So I have two questions.
Sure.
You mentioned that we cheated by like having a BIOS patch to make sure that like all of our servers reported LL or LLT
Yes.
DUIDs to DHCP.
Yeah.
What would you do if you couldn't cheat?
The next best thing you could do is account for it in your inventory system. When you actually get received servers, you need to know, you probably need to keep some track of them for accounting purposes. You probably keep serial numbers, other things like that. If the system uses the UID, for example, there's probably a way to get that from either a label or something else. So you'd have to change your workflow more than we were willing to do at the time. We wanted equality between v4 and v6, and it was possible, so we did. All right, any further questions? All right, well, thank you very much.